My name is Stephen Phillips. I'm the director of the Cal Poly Los Angeles Metropolitan Program in Architecture and Urban Design. Thank you for joining us for our first in our spring 2021 lecture series here, still online in Zoom land. I'm going to begin by introducing Angela Anthony from the Helms District Bakery and Design Center, who's been our formative and most important sponsor over the years. And then we'll introduce Skylar Tibbits, our fantastic lecturer for this evening. Angela?
Thanks, Stephen. Hi, everyone. Thanks, Skylar, for being here. Normally, we would be, like Stephen said, in the Helms Design Center, having a big old party and welcoming everybody into our space. Typically, we host art, architecture, and design events throughout the year, but obviously our in-person events have gone virtual. And so I wanted to welcome you all. Hopefully, at some point this year, we'll be back in person. We'll probably do a little bit of an exhibition at Helms with Stephen and some other architects, and hopefully we can see you all then. So enjoy Skylar's presentation. Thanks.
Thank you, Angela. Yeah, we'll have a number of about 7, 8 more speakers and events, and then we have a big housing event in June that's coming up as well. So very excited that we have Skylar Tibbits. We've been hoping to have him for a while. It's, I guess, in some ways easier now to get someone from the East Coast out here in beautiful California, where he's not going to get to see today. And he's also just, runs this fantastic laboratory, which we'll hear all about today, that some of our students actually are. One in particular, Kate Hayash, was a former master's student with him. So just let me begin an introduction. So Skylar Tibbits is a designer and computer scientist whose research focuses on developing self-assembly and programmable materials within the built environment. He is founder and co-director of the Self-Assembly Lab at MIT, and associate professor of design research in the Department of Architecture. Tibbits has a professional degree in architecture and a minor in experimental computation from Philadelphia University, as well as a master's in design, computation, and computer science from MIT. He has worked at a number of design offices, including Zaha Hadid Architects, Asymptote Architecture, and Point B Design. He's designed and built large-scale installations and exhibited in galleries around the world, including the Centre Pompidou, Philadelphia Museum of Art, Cooper Hewitt Museum, Victoria Albert Museum, and many others. He is the author of several books, very impressive that he does this as well. Self-Assembly Lab Experiments in Programming at Matter from Routledge Press, Active Matter from MIT Press. He was a co-editor of Being Material, also from MIT Press, and the editor-in-chief of Journal 3D Printing and Additive Manufacturing. I'm not going to list all his many awards, which are all fantastic, several. Anyway, it's there online if you want to look. Please join us in welcoming Skylar Tibbits to the Cal Poly LA Metro Program's lecture series. Skylar, all you.
Yeah, thanks so much. I wish I was there in sunny California, and I'm from California originally, so I would much rather be there than cold Boston at the moment. But anyway, I'll live through Zoom and dream about it. So as you heard, I'm Skylar Tibbits. I'm going to talk to you today about our research, some of the things we do at MIT, but I have a few different roles. So one of them is I am the editor-in-chief of the 3D Printing Additive Manufacturing Journal. And you'll see how 3D printing and all forms of additive manufacturing influence our work. But this is just to give one flavor of the things that I'm working on a daily basis. And the journal is interesting to me because it's not just architects and designers, it's material scientists, computer scientists, mechanical engineers, biologists, it's all researchers across the world who are interested in this space. Academically, I direct all of the undergraduate programs in our department. So the undergraduate architecture program and the undergraduate design program. And the design program I'm particularly focused on because we started that a number of years ago, a design minor and now a design major. It became the second most popular minor across campus. And so, we have these brilliant undergrad MIT students that are, computer scientists and mechanical engineers. and they were really fascinated by design, wanting to take studios, but not particularly wanting to be architects, just wanting to be designers of all sorts, like polymath designers, biologist designers, physicist designers, engineer designers, any form of hybrid design in the future. And so we have this really interesting program where we teach all sorts of things from information design to visual communications, product design. We have a food and design studio, interesting academically. But what I'm going to focus on today is our research. So the lab is called the Self-Assembly Lab. This is what it looks like when it's super clean and empty, which is almost never. But you get kind of a visual of the things that we experiment with and the things that we play with. We have many different researchers. Kate is one of these in this sort of outdated slide because she's no longer at MIT. She graduated and now doing awesome stuff after MIT. But we have roughly 15 people at any given time, from undergrads to masters to PhDs to full-time researchers, backgrounds of everything you can imagine, lots of architects and designers and artists, but also computer scientists and brain and cog and biology and material science. And students, researchers coming from all over the world. So to kind of give you some kind of scope here, what we're really interested in is challenging what we think of as smart products, smart manufacturing, smart environments. Typically, when you say smart products, especially in today's digital world, most people will think of the Nest thermostat. Like a smart home means more devices. Or if people think about what is the future of manufacturing, what's smart manufacturing to any of the largest companies in the world, they'll think more and more robots. So smart has somehow been connected with more devices, more robots, more computers, more power, more complexity, and ultimately more failure. So what we're interested in doing is trying to challenge that, to think about how do we really rethink manufacturing? What would true smart manufacturing be without robots and components and electronics and devices that make it more complex? Can it just be about materials that interact with their environment and themselves? Can we think about material properties that are smarter? Can we think about products that are smarter without all of the extra batteries and components and failure in devices? Materials that just respond to energy, respond to our bodies, respond to our environments. And we're specifically interested in very simple materials. A lot of people think about our work, which you'll see over the next hour, and they think of us as a material science lab that we invent these super high-tech materials. We're really interested in dumb everyday materials like rocks and string, fibers, plastics, foams, metals, wood, everything that we have in our physical world around us, and trying to tap into the inherent properties of those materials through different forms of fabrication to augment them. So how I got into this, I have an architecture background. I studied at Philadelphia University, traditional B.Arch 5-year program. And it was right at the time when computing and digital fabrication were coming on board. It was not this early on, but this is the first CAD tool invented at MIT, Sutherland Sketchpad, that then led to the boom in computation in design, whether that's computational design for generation, or it's performance analysis, or structural engineering and environmental, physics simulation. Computation is everywhere in our world as designers, and computation is basically in every other field. So it really became a game changer. Code became a new language for design. And just about the same time that computation was coming on board in terms of CAD tools, it was the first time that a computer was connected to a milling machine. This is 1955 at MIT, the invention of the CNC machine. And that obviously then led to digital fabrication like CNC robots and industrial robots, CNC milling machines, routers, water jets, laser cutters, 3D printers, etc. And so this was really just coming on board as I was graduating, and I became really fascinated in that, and then went to MIT to study design computation and computer science. And we were building these installations around the world where we were writing our own code and running machines and making these mass customized installations, where every part was unique, and sort of flexing the muscles of mass complexity, and sort of drinking the Kool-Aid as I look at it now, that we could build these super complex computational things digitally, and we could send them to machines to fabricate mass customized parts. And this was like 50 feet away from Frank Gehry's data center at MIT, and there's a long history of architects using both computation and digital fabrication to make mass customized parts. But what most people don't talk about is the labor and assembly that goes into these, the blood, sweat, and tears, the long nights, the many student hours and free labor that goes into assembling these complex installations all over the world. We sort of think that software and fabrication is the end of the game. And it became very, very clear to me, and as I was starting to be more self-critical of the things that we were doing, that there's actually a third component, which is assembly, that we really need to think about code for design, code for fabrication, and code for construction. Like, what would the third component be in this lineage? And at that time at MIT, I was working with Neil Gershenfeld's lab, the Center for Bits and Atoms, and we were working under a DARPA grant called Programmable Matter. And this was over a decade ago, and programmable matter then meant robots. Like, everyone was building robots, small robots, medium robots, and I was in charge of building these large robots. So this was about a meter by a meter by a meter, and it could then reconfigure and squirm around the floor and turn from a line into a surface or into a cube. And we built a few of these for that DARPA program. But I started to become more and more critical of this, that, this was really interesting and probably cost like tens of thousands of dollars and worked for a week and then never worked again. And, now it's a dead coffee table in my house, like this most expensive DARPA coffee table you can ever find. And so I started to really think, like, there's a long history of trying to use robotic components in architecture, and it usually doesn't end well. Maybe robots aren't the solution. Like, yes, we want to have better assembly processes. Yes, we want to have smarter components, but in terms of architecture, we need to scale up. We need large things and many parts. And that's where typical robotics doesn't make sense, because cost goes way up, complexity, components go way up, and failure goes up. So we need to think about it through materials. And so that's really the beginning of the lab, and where we started to think about, if we could program physical materials to change shape, change properties, sense, react, we could have a new paradigm for assembly, a new performance for the things that we build. At the lab, we're really interested in these large scale human sectors. And I put this here, to come back to, part of it is because of the background in architecture. We're interested in these scales, like architecture and construction and infrastructure. Now we're working on projects even larger than that, but manufacturing, products, assembly, distribution, like that's the messy human scale world that we're interested in. But I also put it here because this is something that differentiates us. Many researchers around the world are looking at new material properties, or looking at self-assembly systems, like I'll talk about, but they'll be doing it at like a bio, nano, or chemistry and material science scale. And so one thing that's quite unique about our research is the application to these larger human scale systems. And to me, that's really fascinating, because if you look at every other scale other than the human scale, so if you look at the smallest of scales in synthetic biology and chemistry and material science, what's happening right now, and if you skip over the human scale and you look at planetary scales, everything happens from the bottom up. So there is no like designer out there designing planets and 3D printing planets, just like there's no designer designing some DNA strand with a little robot assembling a human. Like, design, functionality, and construction happen through the materials. So all of that emerges through the materials' interaction with their environment and their interaction with one another to build higher order structures. But at the human scale, everything is from the top down. Like, we imagine amazing things as designers, and then we send them to people or robots to build from the top down. And so it's really fascinating to me, like, why that is, and why there isn't another opportunity for design and construction from the bottom up at our human scale. So in the lab, there's three main research topics that we focus on. So the first one, as I was alluding to, is called programmable materials. The idea that we want to take physical everyday materials and program them to change shape, change property, respond to their environment, act as sensors or actuators. We want to make smart materials, but out of everyday materials. And like right after that work on the DARPA programmable matter research, I started this project called 4D printing. And this was really a critique of the previous one, thinking about, what are ways that we could fabricate these smarter structures that is not reliant on robot mechanisms and robot assembly? Could we print the robots all in one go? So essentially it's multi-material printing. Originally it was on a Connex machine, and now we do many other things, but it's different material properties at different places. You can see in the joint, there's this clear material, which is a hydrogel, and that swells with moisture. And we have different quantities of that in different geometries. We print the structure and then we dip it underwater. And so a strand can turn into a 3-dimensional cube, for example, or a strand can turn into the letters MIT, or a surface that can fold into a truncated octahedron, or a surface that can do curved crease origami to create a hyperbolic paraboloid, or a surface that can expand and contract to create double curvature. All of these are not manually formed. They're assembling themselves or transforming themselves just by their interaction with their environment and the geometry and material properties that we've printed. And we did all of these different ones, like 1D to 2D and 2D to 3D, to try to demonstrate folding or curling or stretching or curved crease or expanding and contracting. But after this work, a lot of companies started approaching us, and we started to be critical that it really wasn't about printing. That was the main part here. Like, it was called 4D printing, and that got a lot of press, and we still do some of that work. But the real question was, how do you do this with any material? Why is it that it can work with printing? Can we do it with other materials and other manufacturing processes? And so that became a much bigger umbrella, and that's what we call now programmable materials. It's a much wider range. And we came up with these simple ingredients. So we look at the material properties, and that can be anything from wood to metal, plastic, foam, rubber, whatever it is. You link up those material properties with some activation energy. So wood, we know, is going to swell with moisture. Metal, we know, is typically active with temperature. Polymers are active with all sorts of different things. So you look at some activation energy in your environment or your design application, link that up with the material property you're working with, but pay very close attention to the geometry and think about how are you fabricating that geometry in 2 or 3 dimensions with very specific shapes, quantities, locations, in order to get some type of desired behavior, some type of transformation from one shape to another shape that is based on sensing its environment and activation through the material properties. So this is basically the paradigm that we work within. This is like our method, our approach, or how to do it. And over the years, we've collaborated with lots of different people. This was some of the people in the beginning, like product designer Christoph Gubran, we collaborate a lot with. Mathematician, computer scientist Eric Demain. He's like an origami master and super fascinating person. Materials companies, software companies, a lot of applications companies. And we've worked on a number of different materials. So I'll show you a couple of those. One of them is wood. So wood has a very long history. It's obviously a natural material. It's obviously active. You can look at Japanese joinery or shipbuilding or wine or alcohol barrels. They use the swelling nature of wood to make stronger and more precise joints. But in contemporary times, we sort of resist that, and we try to make wood standardized material as if it was metal or plastic, and ignore the anisotropic properties of wood in our conventional like construction lumber. We don't want it to move or transform. We don't want it to have knots or some weird grain. So we're really not taking advantage of the properties of the wood. If you look at the Eames furniture example, Eames were famous for their molded plywood chairs, but they're not taking advantage of the behavior of the wood to morph on its own. They're really forcing the wood into the desired shape. And then a more contemporary example, Achim Menges's group at University of Stuttgart uses wood veneer that can react to moisture to open and close, which is like an amazing kind of simple advance on what we had seen, but they're limited by the grain that you can find in the forest or the grain that you're given in a specific piece. And so this led to our work on printing wood. because we wanted to take the natural property of the wood, but we want to be able to print it so we can have the full customization of the pattern. And so in the beginning, we were making our own filaments. Now you can buy wood filaments, and they all have different consistencies and wood types and quantities of wood. But essentially, you print different 2D and 3D patterns. You then subject it to moisture, either in that case, submerging it, or in this case, changing the relative humidity, and you can get the wood to transform. And it transforms specifically based on the grain. So very much like the wood in the University of Stuttgart example, we can get wood that folds, or we can get wood that creates furniture-like shapes, or wood that curls into like fish scales. We can get wood to behave in ways that it typically wouldn't. More recently with Christoph, the product designer, we have done a lot of projects around this. One of them was this interesting example where we print these flat pieces of wood, and we print it flat because it minimizes time. There's no support materials. It's super fast and efficient to produce. We then put it in like a Ziploc bag with moisture and then ship it wherever you want. And on the other side, it then transforms into these bowls and baskets. So the shipping is the activation, that we're submerging it as it's being shipped. And then when you release it, it can activate into the shape. And so if you wanted to try to print this, it would be very, very difficult or time consuming, but instead we can print it flat. Another material that we've worked on a lot over the years is carbon fiber. So we worked with a company called Carbitex, who makes flexible carbon fiber. And they wanted to see if we could do the same thing with our 4D printing, but with carbon fiber. So we take these flexible carbon fiber, and in the beginning we print on it, but you can also laminate or spray or bond. You can do all sorts of different things. And we print different polymers onto the carbon fiber in very specific patterns. And then we can promote the carbon fiber to transform based on temperature change or moisture change in very specific behaviors. So that was folding, and then this is like curling or twisting. Based on the pattern that we print, the carbon fiber will behave in different ways, very much like the wood. But here it's just different polymer layers with the carbon fiber activating it to transform based on moisture or temperature. With Airbus, we worked on a component for their engine that brings in cool air to cool the engine. But this component typically causes drag because it's a hole. So they were going to add an electromechanical or hydraulic or pneumatic flap, but then that adds more weight, which reduces their efficiency and adds more potential failure and cost and all these things. So solving the inefficiency by creating more inefficiencies is not a good solution. And so by adding a single layer of carbon fiber, which is extremely light and doesn't add any extra components and electronics and mechanisms, we can control the open and close state of this inlet with a simple material that's activated either by wind speed, which is essentially pressure differential, or altitude. We've done a lot of work on textiles over the years. One of the first projects that we did with textiles was using the pre-stretch. So we take a stretchable textile and we stretch it around a plate. And that essentially activates the material. It's like a jack-in-the-box effect. Then we put it in the machine. You can print on it. Again, you can laminate, you can stitch, you can do all sorts of different stuff. And we print very specific patterns. And those patterns encode the geometry or the behavior of what it's going to do. So here, a circle will change and transform into a hyperbolic paraboloid, like a saddle shape. If you print different geometries, you'll get different behaviors. If you change the thickness or the stiffness of the material, you'll obviously also change the behavior of the textile. And so in this way, the textile is the activation because it has this pre-stretch, and the material is the information of where it's going to transform. So with Christoph, again, we did a project on the future of shoes. It was an exhibition in London. And so we printed this pattern in 2 dimensions that then when you cut out, it jumps into the full shape of the shoe. And we're really trying to critique the assembly of footwear. I've been to a number of factories and it's extremely labor intensive. It's tens or hundreds of components that are manually formed, stretched, sewn, glued together with all sorts of different processes. And in this case, it's a single material composite that can then transform and take all the curvature. The shoe is an interesting one. We've done a lot of projects over the years because the complex shape makes it an assembly problem, which is very similar to some of the things we were doing previously with complex geometry. This is a project we did with Converse where we essentially took CNC knit socks, put it on a last, print in 3 dimensions instead of 2 dimensions, and we print with rubber so that then when you pull the sock off the machine, it is already turned into a shoe. So essentially we take a sock, we print, and that turns it into the structure of the shoe. And the benefit here is that you can ship socks around the world a lot easier than you can ship shoes around the world. And so you can then locally produce the shoe on demand without wasting. A lot of the companies are always questioning, like, do we really want to ship air? Because anytime you ship a box, you ship air. And so they're really trying to minimize the volume. Another advance in the textile space actually came from film. So we were looking at these polymer films, and we were combining them in these slits in all sorts of 2-dimensional and 3-dimensional patterns. We use this bi-material motif. So expansion and contraction cause the film to then morph with very low temperature, like 30 to 40 Celsius. Here we're using an IR bulb. It's almost instant, it's reversible. And we can combine these films into essentially macro scale textiles. And this then led us to realize that we could do the same thing with fibers. And so we did all of this work on auxetics. So auxetics is a term for materials that expand and contract uniformly. So normally when you stretch a material, it shrinks in the other dimension, or when you compress a material, it expands. Auxetics do the opposite. So you stretch it and it expands, which is really interesting for like crash protection or foams or all these other things. But that led to the insight that we could do the same thing with fibers in actual textiles. So we got this grant through AFOA, Advanced Functional Fibers of America. We use CNC knitting machines, and we use both off-the-shelf and custom fibers and yarns. And so then we knit garments, and you can knit an entire 3-dimensional garment with, you know, lapels and pockets and everything, and we can make them active. They can be temperature active, moisture active, or the pink in that case was pH sensing. So you can indicate things, you can sense and transform. And so this is essentially translating what you saw before into the industrial production of textiles. So these fibers are transforming in the same way that you saw our previous work, but here they can change shape and they can change thickness to have different performance. So this project was about a non-reversible transformation for tailoring. So tailoring is a really interesting problem because everyone's body shape is different, and you can either have like couture, like customized tailor, and there's also aesthetic tailoring, like people want to pattern their clothes in different ways depending on, you know, the event or their outfit. If it's about shape tailoring, you know, making customized clothes is kind of expensive. And so that's why we have small, medium, large. We don't have individually tailored things. And so our proposal is you can still have small, medium, large, but then in the store or at home, we can completely customize it so it's an individual fit to the user. And so what we do in this case is temperature active, but we could also do moisture active. And this is the same exact garment on the left and the right. The right is after it's been tailored to the shape of the mannequin in this case. So we can basically shrink it to whatever shape and whatever custom fit profile that they want. It's much like you've probably seen like ski boots or shin guards, or there's different products where you can morph the ski boot to your foot, for example. And so we can do the same thing, but it's embedded directly into the fiber and yarn made through the textile. The second phase of that whole research project was reversible climate adaptive textiles. So not single direction, not about tailoring, but trying to address the challenge that you know, we often need to rely on layering in order to control climate or heavy HVAC systems. So instead, our clothes could adapt to the fluctuations in our body or the fluctuations in the environment. So here we made custom fibers with different polymers, with different cross sections and ratios, and then we can make them reversible, again, either temperature or moisture, in order to morph. So the performance that we're looking for is thickness change for insulation value, porosity change if you want breathability, or vents and flaps also for breathability, or shape change if you wanted some type of like comfort and fit. And so we basically made all of these fibers. We then knit hundreds or thousands of different swatches, ultimately making a series of garments that had these different activation zones that could then morph based on if you walked inside or outside, or if you were super hot or super cold. And they have these different functional zones. So here you're seeing these like gills open to create venting. Here you're seeing like a thickness change, which is like a bellows motif. And so they have these different like functional elements that can transform based on the environment. Here you're seeing again more like slits. At the beginning of COVID, so we were working with a company called Ministry of Supply, who's an MIT spin out. And they're a men's and women's clothing company. They have, or they used to have stores around the country. Now I think they're totally virtual after COVID, but we transformed all of that research towards masks. So at the beginning of COVID, they literally stopped all production on everything other than masks, and they converted all their factories to working on masks. And so we were able to take a lot of the knowledge that we had on knitting and translate that to masks. More recently, over the past summer and then fall, we started working on smart masks that would have two goals. One is to custom fit, because the fit of the mask is really important. And so we could use the tailoring to do that, to get like a custom profile. And then the other is a mask that can sense or detect if it needs to be thrown out, or if it's come into contact with COVID, for example. So instead of having some type of test and having your PPE, the PPE can be the test. And so we did a bunch of research over the summer and fall around that. So then the second category of research is on phase change systems. So phase change is about materials that go from solid to liquid and liquid to solid. So instead of shape change, we're looking at property change, essentially. And from the early days in our 4D printing work, we were always trying to critique existing 3D printing technologies. And, talking about the journal, I'm very much interested in that. And there's this spectrum from like very low end DIY machines to like super expensive high end machines. And we were working on our 4D printing work with Stratasys on these like, $200,000 machines that are very black boxed. And if you mess with anything, you like void your warranty or you damage this super expensive machine. But if you go to the other end, you can't really customize it because the quality is not there. They're just so low quality and low cost. So we were really interested in this kind of hybrid model. And at the time we were working with Steelcase, and they came to us with a problem that basically 3D printing is irrelevant for furniture. If you look at true manufacturing scale, it's just too slow. You can't really print a chair in any production speed or scale. So could we rethink that? And so we had developed this new process called rapid liquid printing. So in rapid liquid printing, it's a vat of gel. And in that gel, we then draw in 3D space like calligraphy. And we extrude out different materials. Those materials cure underneath the gel. So the gel is just acting as a support material, essentially eliminating gravity. So we can draw in 3D space, we can change shape, we can change speed, like calligraphy, we can extrude with different line weights, and the material cures under the gel. We then pull it out. The gel is 99.9% water. It's non-toxic. We wash it off. We can print with foams, rubbers, plastics. Here you're seeing us print inflatables. We can print like soft robots with complex chambers, all sorts of different behaviors. We worked with a lot of different companies on this. This one was with BMW, looking at the future of the car interior, specifically like cushions and foams. And so we were trying to think about what if these foams could have all of the function of the car seat into one. So, you have massage features and lumbar support. You have crash protection features like airbags. You want to mold to the shape of the body. You want to change stiffness on the fly. So can we have one material composite using a printed soft robotics system, essentially, that can then morph based on pressure into these different functional zones? As I said, we've done a lot of other work. This is with the product designer Christoph Gruberon, and we did a whole series of home goods, from chandeliers and wall sconces to pendant lights and toothbrush holders and vases and all sorts of different things. We've exhibited these around the world, and then more recently we've spun out a company around this printing process called Rapid Liquid Print Co. And they're now trying to scale up the printing technology. And actually, Kate was early on. She's an inventor in that process. And so we've tried to keep in touch with her about that. And a lot of the progress was made through many of the researchers in our team. One of the things we started to challenge was that we can do silicones and foams and plastics really well, but we can't do high temperature. And so then we advanced that and we started to print into a powder bath instead of a gel bath, and we can print with molten metal. So this is a new process called liquid metal printing. And we literally print with liquid molten metal into this powder bath. It's even faster because the metal cools in seconds. And so you can print, meter by meter structures in seconds and pull it out, and you have large scale metal objects. And so this has been, over the past couple of years, a big advance and a big focus of our work. We're working with automotive companies and a number of other people in developing the metal printing aspect. But to me, one of the most important parts here is that it's fully recyclable. So everything you print can be directly put back into the machine, melted down, and printed again. There's no like middle step. It's just one-to-one, which is super, super nice and interesting to me. Another aspect of phase change is a principle called granular jamming. So we became really fascinated in this. You've probably seen granular jamming if you hadn't heard about it. So when you're at the beach and you jump on the sand and it hurts, but when you play with the sand and it's soft, that's granular jamming. Or when you get coffee at the grocery store and it's in this like brick and it's really hard, but when you open it and it flows, that's also granular jamming. So it's basically granules, particles that get stuck, they get jammed. And when they're stuck, they act like a solid, but when they can move, they act like a liquid. And it's this really fascinating phenomenon to physicists and material scientists because you don't need temperature change to change the phase. And it's totally reversible. You can go liquid to solid instantly whenever you want on demand. So it's a really interesting scenario, and it's so simple. So we've worked on things like crash protection, or this is an adaptive acoustics panel with Google that we're doing. And we did reversible packaging with Steelcase based on some of this stuff. But the most interesting one to me is a new construction process that we did in a collaboration with Gramazio Kohler's group at ETH. And the backstory here is we were at a conference on jamming. There was like just people on jamming at this conference, like mostly nerdy physicists and material scientists looking at jamming. And they invited a couple of architects. Gramazio Kohler was one and I was another. And we then started to think like, what can we do with this? And we were thinking, this is essentially reversible concrete, but we need to make sure that we have no bladder, like no membrane and no vacuum, because that's typically how it works. You pull a vacuum on a bladder full of particles, because that would be too energy intensive and too susceptible to puncture. So we came up with a way to combine rocks and fibers. And just by loosely combining those two without any adhesives or connectors or bolts or screws or anything, you can promote jamming. So at the Chicago Architecture Biennial, we had this yellow box where we put rocks and string, rocks and string, rocks and string. The robot is spitting out the string in very specific patterns. And then the rocks fall away that didn't have string. So only where there's string does it jam. And that's where the robot was printing this pattern of string. And it jams and becomes load bearing. So we put 3 tons on top of the structure. It's totally solid. It'll feel like a brick wall if you run into it. But yet when we reverse it at the end of the exhibition, we can just wind up the string and it disintegrates into a pile of rocks. And so the reversibility is really important to us because, concrete, the problem is, well, first of all, it has a cure time. So you wait 30 days on site while concrete is curing and you can't really do anything. And the second is that it's wasted. You can't reuse it. It's not a modular system that can be taken back down. And so, in terms of recyclability, it's really terrible. It's also not great for the environment. And so having reversible structures for concrete is, really important. More recently, we advanced that to make morphable structures. So we do the same thing. We jam the column, but then we post compress it. So we basically compress this column. We can then rotate it and turn it into a beam, which it typically shouldn't be able to do. You can stand on it, walk on it, load it. And then when you take the compression away, it then disintegrates as if it was a pile of rocks and string. And so instead of loading it from the top like a column, you can also load it as a beam and you can rotate it and make modular components. And that's simply by compressing it and holding that compression. So We also did a wall that turned into a slab that then you can disintegrate. And more interesting, we demonstrated that you can make a bending beam. So you make a column, you compress it, you rotate it, and then you can continue to compress it, but off axis, and then it can morph. And so this is what's super interesting about jamming, is that it has a semi-solid state. So it's not only solid to liquid instantly, it also can be sculpted. So it's sort of like a clay in that way. And you can tune it. You can decide when you want to undo it. You can decide when you want it to be solid or when you want it to be soft. And so we've done a lot of research over the years on that. And then the last category of research we focus on is self-assembly. Obviously, as the name suggests, we're interested in how individual components come together without humans or machines. And we started this work with a colleague of mine, Arthur Olson, who's a molecular biologist. And so we built this project where you shake it hard and it breaks, but you shake it a little bit softer and it comes back together. And this was modeled after the polio virus and a tobacco plant virus and various other biomolecular structures. And we were trying to show that non-experts can build precise things. So you don't have to have any skill. You don't need to know what you're assembling. You don't have to have the blueprints. You can pick this up blindfolded. You can have no idea what it is. And all you're doing is giving it random shaking and it assembles the same thing over and over and over again. So all of the information is in the parts, not the people. And over the years, we've experimented in many different environments. So this one is underwater. Here, we're trying to push the question of what if you have unique components? So each one of these components is different. None of them have the same geometry, and they also have different lock and key mechanisms. So each one, there's a different pattern and only one complementary match can be found. So it has to search for that complementary place in order to build the chair in this case. And this was important to us because we could show that you can make arbitrary human designed things still using self-assembly. Like a lot of people would think, either self-assembly is only at the smallest of scales or self-assembly is only for buckyballs and, radially symmetric precise geometries, but we wanted to demonstrate that no, you can do self-assembly for anything, even arbitrary things like chairs. Not that you necessarily would, but you could demonstrate that this is a viable manufacturing process. At the largest of scales, up until a couple of years ago, we were experimenting with self-assembly in weather balloons. So these are meter diameter helium-filled weather balloons. And interesting, at each node, there's Velcro node. So it's not magnets, it's not surface tension, it's not adhesives like we had used in the past. Like you always need some type of stickiness. In this case, we showed that it can be Velcro. So it doesn't have anything to do with the pulling force. It's really about the patterned attraction. And so we had people over, we had these fans in the courtyard outside of our lab, and we had these helium balloons floating around, and we shot this over the course of a couple of days, and they made different patterns. They make cubic lattices and they make things like beams. These are all truncated octahedrons, and so they make these lattice structures. And what's interesting about this to us is that we could potentially build in the airspace. So we were interested in trying to tap into natural forces of energy, in this case, potentially wind, or other spaces where we can build. It kind of hints towards the critique that, most people say, well, why would we do this? Because we're really good at building in a construction site, or we're really good at building in a factory. And the very obvious answer to that is there's a lot of places we're bad at building. So think about extreme environments, think of outer space, think of underwater, think about dangerous places, think about places where it's hard to get materials, hard to get people, like remote places, think about urban construction sites. And so there's a lot of interesting scenarios where you need to rethink the way we build. And so one would be that we could build up in the air, let the helium then die, and then the structure comes back to the ground and you get this much larger space frame structure. But up until this point, we were experimenting with different aspects of that, thinking about assembly. We then started to look at replication. So what if you could take simple components? These are literally just plastic spheres with metal pieces and magnets inside and very specific geometries. And they promote these different cellular structures. And much like cellular mitosis, they grow and divide over and over and over again. And what you'll see is that they can encapsulate things and they find stability points. So like 5 or 6 of them are very, very stable. As they grow too large, then they have to divide off and they then form these much smaller stable structures. And so you can keep adding food, which is essentially more and more components, and you'll continue to grow and divide, grow and divide. So we were interested in not only just showing that you could assemble repetitive structures, but you could show unique individualized structures. You could scale this to large structures, and you can potentially grow and divide or show sort of low level replication. But up until this point, this was very academic, and we would think of this as sort of basic research. You know, there's basic and applied research, and basic research is usually like asking fundamental questions and trying to understand the universe or understand fundamental things about our world and gain, you know, scientific principles. Whereas applied research is taking that research and applying it in novel ways to different problems. But a few years ago, we were approached by a group in the Maldives. They knew our self-assembly work, and they were interested in us coming out to talk about some of the challenges that they were facing in terms of sea level rise and climate change. And so we started to try to understand, like, what are the typical approaches that people have in terms of sea level rise? And the first one is to build barriers and walls, essentially fighting the forces of nature. The second one, and the most common one, is dredging. So in dredging, essentially they'll go to the deep ocean, they suck up a bunch of sand and they pump it back onto the beach. But the problem here is that it doesn't solve the problem, that it actually just becomes an addiction, that year after year after year, you have to keep dredging because you don't understand why your beach is eroding in the first place. And it's super damaging for the environment and the marine environment. It's super energy intensive. So it's really not a good solution. They do the same thing. They can build artificial islands in about a month through dredging, and that's, you know, their main economy is tourism. And so they build artificial islands, and even in natural islands, they use dredging to try to sustain them. But in the exact same time that it takes them to build the artificial island through dredging, 3 sandbars built themselves. And these are, you know, very large quantities of sand. Like, you could live on these islands. That, you know, you can park a boat on it. A lot of the locals will go there for a day as a little mini vacation. Like, these are large quantities of sand that emerge in the course of a month or two. They'll be there for some period of time and then they'll go away. And we went to a number of these, and that sort of sparked the interest that, like, this is already happening. If we can just tap into this natural phenomenon, like, why does sand accumulate? Why does sand self-organize into these structures when it does, where it does? And if we could understand that, we could use that as a sort of natural collaboration with the forces of the ocean. And so we started to study these different patterns of why sand accumulates in different structures based on, like, the topography or bathymetry under the water, or different shear forces and currents and tides. And so what we're proposing is to work with the forces of nature to build rather than destroy. Like, normally we hear of natural destruction, we're talking about natural construction. So we built in our lab a big wave tank. We pump a bunch of waves, we place different geometries underwater, and then we try to study what kind of accumulation results from those different geometries and wave patterns. And so we've done hundreds of different experiments with different geometries, different materials, different strategies to try to accumulate sand in different areas. We then now have done 2 field experiments. We did one where we built it at MIT. We did the exact same geometries that we saw in the tank. And it was roughly like 3 to 4 meters by 3 to 4 meters by 2 meters. Then we did another one. This is the largest one we've done so far. It was 2 bladders, 10 meters each, so 20 meters long by 4 meters by 2, so fairly large. This is one of the bladders, and it's made out of this textile material and placed underwater. So this was in 2019. So basically, we take the best of what we see in the tank, we scale that geometry up, we locate a place in the lagoon, and we went out there and installed it underwater. And then over the course of months, and now it's been a year, we monitor it through both physical measurements, drone photography, video, and satellite imagery. And so we try to understand how did the sand accumulate in relationship to what we saw in our tank. So over the course of a few months, we saw a significant amount of sand accumulation with this second field installation. And it's roughly a half a meter by 20 meters by 30 meters. So it's a really significant amount of sand that accumulated in a very, very short period of time. And what's interesting here is how targeted it is. And so you theoretically could strategically place these almost like gardening with sand in certain seasons, because they have two predominant seasons, a northeast and a southwest season. And so essentially you don't know exactly what the waves will do, exactly where the waves will be, but you generally know in this season that you could utilize the force of the ocean to accumulate sand in strategic areas. So very much like on the East Coast here, you know, we have hurricane season, we have nor'easters. So you can generally understand which direction the force of the ocean and winds are going to be, and you could try to utilize that to accumulate sand. The bigger vision is that we can make these adaptable, so both adapting to the demands of the location and the changes in the environment, whether those are seasons or storms, but they're also submersible, so we can inflate and deflate, and basically like a submarine geometries that we can place and deploy when you need them. We got a National Geographic grant, and we're supposed to go 2 more times to study the same location. And then what we're trying to do now is build a larger community across the world to try to test this in many different locations. And so, you know, we'd like to team up lots of different people, both island nations and coastal locations, and try to collaborate to try to solve this in a way that's not about building walls or dredging, but rather is about working with the forces of the ocean. So where is all this stuff going? So I talked about in the beginning our interest and my background in architecture and our interest in the human built world. And essentially what we're trying to do is critique what we think of as smart materials, smart products, and smart manufacturing systems. We're really trying to challenge that, you know, if you call a smart product smart, but yet it fails quicker than the dumb product, I would say it's not that smart. You know, or if it takes more energy, it costs more, and it fails more often, we really can't call that smart anymore. So we need to rethink that. Yes, we are all interested in making better X, Y, and Z, better buildings, better clothing, better shoes, better cars, but we need to do that with less material, less complexity, less failure, less energy, less cost. We need to be able to do that with material properties. And we're also trying to critique the notion that the future of construction and manufacturing is robotics. You know, almost everyone will say that the future of construction and manufacturing is more and more robots, drone robots, industrial robots, you know, humanoid robots, whatever robots you can imagine. But in my experience, that may not be the case. In the very simple example, you could say, sure, there will be more robots in the world, and that's probably true in the near term. But even if that's the case, we should still be tapping into material properties so those materials can collaborate with robots. They can sense, they can activate or actuate, they can respond to the environment. Materials are very, very good at nature. Materials are made by and responsive to physics. Robots are very, very good at not being tired and repeating things precisely. And humans are very, very good at creativity. And so by collaborating between those three, you can have a kind of much more symbiotic relationship to achieve things you couldn't have done with only one of those. But if we go back to that DARPA Programmable Matter grant, almost every one of the researchers about a decade ago who was working on robots is now working on materials, whether those are soft robots, whether those are multi-material printed and 4D printed structures, or it's synthetic biology, or, you know, growing structures, or many other things. Much of the robot community has shifted towards soft, flexible, agile, smarter material systems. And I think there's a reason for that, that the electromechanical notion of what a robot is shifting towards a material notion of robots. Materials can sense, react, transform, have logic. Materials are the future of robots. It's not the clunky beasts on the left, it's the agile, flexible things. And if you look at any one of us, I mean, intelligence doesn't come from computers and chips. Intelligence comes from matter. Like, all of us are materials. We are not robots. So we believe today we build smart robots and machines. Tomorrow we build smarter materials and environments. So thanks so much. So I will stop sharing my screen and we can do Q&A, I guess.
Yeah, thank you, Skylar. That was awesome. Obviously, it's extremely polished and well thought out. And I actually thought it was interesting how you almost answer all the questions one might have as you're getting into it. I know the students are going to have a number of interesting ideas surrounding your research. You're very, it's very timely, very thoughtful, very exciting, very nuanced. I mean, I have several questions, but I'm going to just start with one that I think you almost answered, but don't quite. You're doing this amazing research, study, and analysis with enormous resources that not a lot of people get the opportunities. So, first of all, congratulations. I know that wasn't an easy life effort to chase after that and be able to do what you do. You're also really thoughtful about it. I started wondering, I think about people like Elon Musk and I go, well, we all know he's chasing after Mars, right? He wants to go build cities, go grab resources. You're doing something different. And I know you come out of architecture and you kind of answer sort of where you think this is going in terms of the future of architecture. I mean, we obviously get sustainability. You're looking for more efficient systems, better building fabrication technologies. But then I also kind of want to know what motivates on maybe that sort of meta question where you really think this work can achieve, because it's really fantastic. And I'm just wondering, maybe on the larger expanse, what you think might come out of it.
Yeah, I mean, there's probably a lot of answers to that. There's like personal fascinations and interests, and then there's like larger impact driven goals, and then there's more like responses and critiques to ourselves or to the field. You probably heard in every one of the projects, it's almost like a criticism of our own previous work. Like we make every one of them outdated in a way, and we're just like, that was really dumb. Why did we do that? And then we like do a better project or what we think of as better, and like keep critiquing it. And we try to do the same thing about whatever field we're in or whatever industry we're working in. We try to think of like, that there's got to be a better way to do it than that. And so there's that, and that like drives the work. So every project has 10 new projects, and like it keeps driving. So there's that exploration of the work, and then there's like that same kind of question in terms of construction and architecture, like whether that's residential building construction or whether that's like commercial and skyscraper infrastructure. Just spend any amount of time, and I've spent a little bit of time in that industry, and I've done all sorts of projects independently in residential stuff, and spend any amount of time, and because you're probably an outsider, like you're not literally the construction worker working there, and this isn't your day-to-day, you have enough separation to just be like, really? Like, that's how we do it? Like, that's the way we build today? Like, that is insane. And that is the same kind of mentality that we typically have when we go to a factory to see shoes, and we're like, that's how you make it? Like, you think that's a good idea? Like, that's what the best you can do? And I'm not trying to like, I don't know, make a joke about it or like be an ass about it, but because you have this outsider lens, you can really be like, come on, there's got to be a better way than that. I'll give you one super simple example. They make lasts. So in the footwear space, there's like a last, which is called like, or I don't know why it's called that, but it's like this 3D shape of a shoe or of a foot. and they make all their shoes around it, and it's super highly proprietary, and there's like these one people in Italy that like hand carve these lasts, and Nike's got their last, and Adidas had, and it's like this whole thing. And when we first started working with them, they were like talking about this and like, are they going to send us the last or not? Because I'm like, what are you talking about, man? I can print that in like 5 minutes. Like, what? This is not a thing. Like, that's not a problem. That's not, it should not be an issue in your industry. Like, anyone can make any shape last anywhere at any time. Like, and it's just because of this legacy that has been built up. That's just always how they did it. That is a problem. You know what I mean? And like, there's so many of these examples in whatever industry. And so I'm like super fascinated by all of those things. And like, you can find it anywhere if you just stop and think and just like be self-critical, and also like critical of the way things are done because of like strange legacies that emerge. And so in the construction industry, I'm really interested in that, like just rethinking the way we build, whether that's like reversible concrete, granular jamming, or building in the air, or building with the ocean, or, you know, just like really different approaches to thinking about how to accumulate things. You know, in the longer, bigger term, the Maldives work to me is like the most important. I mean, that I can see that being just like the life's work, in that like it's, I mean, this is like decades worth of research. We're barely scratching the surface of what's possible, and there's a lot more that we need to do research wise, and a lot more to learn, and it's a super complicated problem. But it's the first time where it's like a problem that is so important that it's bigger than like any weird nerdy issue that we've been talking about. You know what I mean? Like, it kind of was just like, whoa, this is where it all matters. Everything else, it didn't matter. Like, we thought it mattered, but it didn't matter. Like, now it matters. You know what I mean? Like, this is, people are gonna live and die because of this problem. You know what I mean? You're seeing it like right there, that this island will go underwater. You know what I mean? And so that's where I was like, this is important. This is a very, very important. It's fascinating. It's super cool design wise. It's amazing collaborators, amazing location. Like, I could nerd out on the lab stuff all I want, but like, this is the first time where it was like, this matters. And that, you know, I think was really important. All the other stuff I think matters, and we're trying to solve all these problems, and they're big, but you know, that one was inspiring because it just became like a whole nother realm. And so, you know, I'm particularly passionate about that, and think that it can lead to something much, much larger, you know, trying to tackle this global problem of erosion and sea level rise. I mean, there's really no solution. Like, ask any of the experts in the world, like, what are you going to do about sea level rise or coastal erosion? It's like, run away. I mean, move, you know, like, or build a big wall, but that's not going to work either. There's literally no solution. And so, you know, to me, this is like the most important thing that we could be working on.
So you're really interested in the environmental questions of our world, which is cool. Does someone local, like in the one of our students, have a question? Just go for it. Here's your chance.
I had a quick question, just regarding how students like us, per se, people who don't necessarily understand the materiality and how these things function, how we could become a part of this process and how it starts to be introduced into everyday architecture.
Mm-hmm. Yeah, so the first part of your question, just play. I mean, a lot, as I was saying before, people think that we're a material science lab, and we're like, we don't know anything about materials. The only thing we know about materials is just by playing with them. I don't know anything about the molecular structure of the what's and this and that. So like, you know, we just play a lot. We just make stuff and try. And then we do learn. I mean, obviously I'm sort of joking, but like, we do learn a lot of these things just by going into it and by being fascinated and being like, wait, why did that happen? And then you like try to figure out what happened there. And then you learn a little bit more about, you know, this polymer combination or this, like, you know, melting point, or I don't know, whatever it is. But almost everything we do is like, have some big idea or even a small idea, have some radical proposition, like have a hypothesis, and just make stuff and test it and build and play and break it and experiment and just like dive in. And everything is like empiric in that way. Like we empirically test and learn and build, and that gives insight. And you know, sure, there's lots of room for computation and simulation and doing better than just like iterative testing. Like I totally believe that, but I think there is no substitute to just learning by experimenting and playing and doing and making. And you know, this also goes back to like why a lot of the stuff that we're doing was already here when we were a craft-based society. Like before industrial manufacturing, if you look at like, you know, woodworkers or metalsmiths or like textile people, they knew everything we're talking about and tapped into it all the time. But we lost a lot of that knowledge when we went to industrial manufacturing and assembly lines because everything had to be standardized. We don't have the time for the nuanced understanding of this material and this craft-based knowledge. Just like, just crank them out, you know, like keep going. And we lost a lot of that inherent knowledge that people had by intimately working with these materials. But what's amazing is that it's coming back because we have digital fabrication. We now can tap into those material properties and we can produce at efficient scales and speeds, but also tailor and customize to either material properties or, you know, some other demand. And so I think that's the unique opportunity, but, you know, nothing beats playing and learning by doing. And so that, you know, almost even in the Maldives, like it's super hard because it costs a lot of money and it takes a long time to do an experiment in the Maldives, and you have to wait a year to see what happens if it worked or not. But we built a wave tank and poured sand in it and like got the sand from the Maldives so that we could have exactly the same sand and like try to, you know, pump waves and study like what happens with different patterns and just do thousands of tests and try to get some intuition for what's going to happen. Sure, we can use simulation till you're blue in the face, and we do some of that, but the problem is that those simulated models are often no better than the physical models that you're building. And many times you spend all your energy trying to calibrate it and you don't really get there. You don't build the same intuition with just playing with the material. And so, you know, I think that's the easiest way to get in that. You know, how does it influence the architecture, or like how does it enter architecture? You know, unfortunately, I guess I'm a little bit pessimistic about the construction field, let's say, because if you know, we work with a lot of different industries and we do some stuff in like the AEC space, but the problem is an incentive problem, I think, because if you look at like footwear or apparel, it's a marketing driven and performance driven industry. So the incentive to innovate, to come up with new materials, new manufacturing systems is either because of marketing dollars, like look at Flyknit, you know, or it's a manufacturing performance, like I want to be able to make shoes faster, or it's an athlete or consumer performance, like I want to be able to run faster. Like there's a clear demand and there's a payoff for them to innovate, go better and better and better. And they also compete, like Adidas has to beat Nike, has to beat Reebok, has to beat New Balance, whatever. You know, if you look at a lot of other industries, it'll be like purely safety driven, like think of aviation or fuel efficiency, or it'll be like performance, fly faster, be lighter, you know, drive faster, drive safer, look cooler, I don't know, whatever. There's all these different incentives. And one of the drivers that like automotive has is they have the concept car. And the concept car is super important, I think, because it basically forces all of the companies to put their best idea out there. Like, what do you think the future is going to be in 5 or 10 years? Like, put yourself on the line, show us what you got. And then people will say whether they like it or not. And they're held accountable. Like, did you make it happen or not? You know, and they have to show each other. But the footwear space does some of that stuff. Like Adidas Futurecraft is starting to do that, like put things out there without saying I'm going to make 1 million pairs, but just do it and show it's possible. Make 100 pairs, show Nike what you did, you know, like show your competitors that you did it. And then they start to like feed off of each other, and that drives innovation. But the construction industry doesn't have any of that stuff. Their only incentive is basically to not get sued. You know, they don't have the same incentive to try to like, they don't have the marketing stuff, right? The best thing that they could do is do exactly what they know. because anything they do otherwise is riskier, or someone might get hurt, or it might take longer, or they might lose money, and their margins are so small. So it's really hard. So what ends up happening in construction is that all the innovation has to happen around it, and then it has to trickle back down. Like if you look at composites, that came from all the other industries, and then it slowly makes its way to construction. I hope that's changing, and like hopefully we can be one group that pushes, and there's lots of other people out there that are trying to push, and now you'll see like the Googles of the world that are like trying to push on the construction front too. So I hope it's changing, but that's the challenge with any of these innovations, is like trying to get them into construction is so much harder than any other sector.
Len, you had a question.
Hi, Skylar. First of all, thank you for the lecture. So I actually have two questions. I'm really interested in 4D series, and I guess like the question comes, what is the fourth dimension for you? Is it similarly as it was defined by Kipnis? It something has to do with time, or it's more like speed aspect? And what is the general impact on the performative aspect of your project and studies? And the second one is, since like you talked a lot about shoes in the last couple of minutes, so I got a question. Have you ever, I guess you did, have you collaborated with United Nude?
No.
No?
No. Obviously we know them, but no, we haven't collaborated with them. Yeah. So the 4D question, so I should have said it, but the reason we said 4D was because we were taking three-dimensional printing and adding the element of time, that we wanted to print things that were transforming over time, that it wasn't printing static things like we had typically seen. You know, at that time it was all like, you know, desk things, or like toys or paperweights, or, you know, static objects. And so like, you know, we didn't want to print these static things. We wanted to print active things like the reconfigurable robots and all the programmable matter work that we had been doing. We wanted them to literally be active, to change over time. And so that's why we said 4D. But, you know, there's multiple definitions of what the fourth dimension is, and some people are like, you know, you're not 4D printing because it's not a hypercube, and you know, there's like 4-dimensional stuff. But we were referencing the kind of common understanding of 4 dimensions, meaning time. Yeah.
Thank you.
We have a couple questions from the audience, which we should take, and then come back to anyone who has questions. But Tibby Dunbar, from one of our sponsors from Boltap. Tibby, you've opened you up. You could speak and ask your question if you want.
Hey, Skylar, this has just been amazing. Really mind-blowing. And as I was watching your computations and your materials all self-manipulating, I just had this visual, and I guess in some ways the first question from the student is maybe a question to prompt experimentation and play. Is I suddenly thought, well, eventually could a building build itself? And it's really sort of it's a far out question, but it was just based on the visualization that I got as I was watching your materials self-assemble, and I thought, well, is it someday that a building will just materialize in front of us just by the fact of these materials being able to do this by bonding together and reacting?
Yeah, I mean, in the beginning, we were doing all this research, as I was saying, on self-assembly, and you know, we had sort of the naive perspective with the robots, like, okay, yeah, we could build any structure, like make a bunch of super smart robots, they'll climb each other and then build this other robot structure. Pretty quickly, we sort of self-critiqued and, you know, also failed at building crazy complex robots, and started to think like, maybe that's not the way to go. Then we were doing all this more like basic research, trying to understand, why does self-assembly work without robots? You know, what is the phenomenon of self-assembly, and how far can you push it for construction? And, you know, the closest we went at that time was like the balloons, making these, you know, I don't know, 10 by 10 by 10 lattice structure kind of thing. And I thought for a while that it would stay in that realm, like it would stay this basic academic research until the Maldives project. And that became like a whole nother scale. And in some ways it like shifted over building scale and went to like landscape, you know, geography, like infrastructural scale. And in many ways, it makes more sense because if you think about, you know, the formation of planets and mountains and caves and, you know, all sorts of other things that are like many times bigger than buildings are formed through the forces of nature. And so it makes a lot more sense to build with land, you know, whether that's sand or whether that's rocks or, you know, whatever other materials of the earth and the forces of the earth. So certainly can large scale occupiable, like inhabitable structures build themselves? Certainly. And that, you know, go to your local cave, you know, whatever, like you definitely can make architecture. Like one of my colleagues, Anton Garcia Abril, you know, they have this like cave structure that they're now turning into some amazing house. Yes, so architecture can be made by itself. You know, will it be the architecture we're used to? Probably not. And I think that's the problem is like, you know, you're trying to fit like the square into the circle, and it like, can you make the buildings that we know of today self-assemble? Like maybe, but that's probably not the way we want to go. And, you know, maybe Gramazio Kohler's like drone assembled architecture or flight assembled architecture is a smarter way to do that, because it's like, you know, have a very specific robot with a very specific task to pick and place components and be able to assemble structures. And maybe that's a smarter way. You know, I'm just as interested in that kind of bottom up assembly, but it's not, you know, pure self-assembly in the sense that we've been looking at through materials. So I think it just depends on like how we change the definition of what we know of as architecture. I mean, is the jamming research self-assembly? You know, it gets pretty close. Some of the work, so one of them I didn't show, we did this project where you basically have a mold, you pour rocks and loose coconut husks into the mold, and you can then slip form it. So you can move the mold as you go. And after you pour, and then you're left with load bearing structures. You don't have to precisely place it with a robot, for example, it's just pouring it. You know, I think there's a lot of interesting things like that. There's also work on like growing architecture, you know, whether that's through mushrooms or many other things like that's in crystallization. Like there's lots of other aspects on how you could self-assemble large scale structures. So, you know, I totally believe we can. They likely won't look like the buildings that we know of today. And they maybe are still going to be like super niche applications for building in very specific environments with, you know, specific resources. You know, is it better to build the buildings we know today on the moon, or is it better to self-assemble structures like we're talking about on the moon? It's probably smarter to self-assemble them. So
great. Susan Stolting, you had a question, kind of an interesting environmental one. You can speak if you unmute. Maybe we go to Angela. You want to ask you had a question?
I did have a question. Hi, Skylar. Thanks so much for this presentation. It was really, really interesting. You talked a little bit about this topic of utilizing the tech and the materials in a somewhat of a predictive way. So whether, you know, needing to change the temperature changes and adjusting the materials to that. And I'm wondering if there are other applications that you're researching either in architecture or in healthcare, for example, in more of a predictive way, you know, whether that's predicting the need for the building to adjust to maybe an earthquake, or predictive in healthcare and preventative.
yeah, great question. And almost everything I showed, especially in the programmable materials section, is prescribed on what's going to happen. And I'm not necessarily like fascinated by that, but that has emerged for a certain reason. So like, for example, in the 4D printing work, we did some work on like printing strands that transform into proteins. And I don't ever show it. I mean, we have videos of it and we've, you know, shown it before, but I don't like use it because you don't know what a protein is supposed to look like. So it transforms into like a big hairy ball mess thing. And you're kind of like, cool, did it work or not? And so like the demonstration of letters MIT or an octahedron or whatever end up being a lot more useful to understand for ourselves and to convey the project to someone else, to show that it can do something that has been predetermined. Like, for example, the same thing with the chair. The reason we did the self-assembly chair was to show that, like, yes, it worked. And we're often up against that, you know, whether it's like for a publication or an exhibition or even ourselves. Like, a lot of times we don't even know if it's working unless we are able to have some indication of, like, did it do the thing that we thought it would do or not. But that's, like, you know, very early in the spectrum of what I think is possible, and probably the least interesting, because in a way it's top-down design with bottom-up assembly. It's much more interesting if you have bottom-up assembly and bottom-up design, where the design emerges through the process, but you can quickly get into chaos and things that you can't recognize what's happening or not happening, or it can go out of control and then it's, you know, less useful. So you have this really interesting spectrum. You know, I'm really interested in the true collaboration with the material medium, that I may not be able to understand what the best design is at any given time. And I think the medical application is super ripe there. You know, we've worked with a bunch of people in the medical space, and I remember specifically talking to some surgeons. And by the way, the 4D printing work that we've done has, like, totally taken off in way better ways than I could have ever imagined. There's, like, entire fields of people just doing 4D printing with, like, conferences and journals just on this. Like, you know, I'm not even anyone in that field anymore after we introduced it. And almost all of the awesome applications are in the medical space. I mean, that's where it, like, totally took off. And I never would have guessed that. I was not thinking about that. Like, that wasn't on my radar. And it's, like, the best application you can imagine, because these surgeons were saying, like, look, everyone's body is different. It's a really harsh, complex environment. It's really hard to get into the body. You don't want to be invasive. Every solution is unique. And so it's, like, perfectly suited to be able to deposit something and allow the material to solve the local problem. You know, the surgeon, I don't even need to know how it solved it. I just want it to solve it. And I want it to be smart enough to be able to do it. And so I want to be able to print systems that have some embedded logic that, like, if this happens, if that happens, and you can, you know, build more sophisticated, essentially functional circuits that can then solve the local problem in a customized way. So, you know, I think that's the one end of the spectrum. Then in, like, the Airbus collaboration, you know, they're very much like, it needs to be here or here. There's no, like, I don't know what's happening when it flies. You know, like, if you're in a plane, you don't want to, like, oh, the wing magically found this awesome shape that, you know, like, you need to know it's here or it's here, you know, at whatever time and whatever state. And they need to totally understand that it's, like, a two-state system and total control, but it can do it itself. It just needs to be there. And so that, you know, shows you the entire range of what's possible, from, like, totally prescribed and solving this problem through material performance to, like, totally open-ended collaboration with the material. And the material can both respond and, you know, maybe potentially predict what's happening. So I'm much more interested in that space that you're hinting at, but it is both, like, technically really challenging. And so, you know, we slowly climb the mountain to try to get to more and more sophistication. And also often really hard to understand and or demonstrate, because you get to a much wider space of possibilities. And so anyway, I think that's, you know, super fascinating, but definitely, like, harder to do.
Susan has a question that I'm gonna ask because she doesn't have sound. So she's wondering, obviously, that you're influencing currents and the accumulation of sand. And she's wondering if you're, you know, how are you influencing other life forms, for example, say migration paths, weather patterns. And then she asked a tough question, do you think you can correct natural disasters or even create them?
Yeah, I mean, this is a really interesting one because, you know, you'll hear of things like cloud seeding, for example, and that's, you know, generally thought of as a pretty bad thing. And a lot of that was happening, you know, in the Beijing Olympics, I think, and, you know, the US military has done, but so there's like a long kind of dark history of humans trying to control nature. And so, there's many other examples of this kind of stuff. And then it quickly gets into like GMOs and like genetically modified organisms and like lots of other things there. And so this is like a very complicated ethical question, is like, how much can we, I call it collaborate, because we're not trying to control the ocean. We know we can't control when waves are coming and storms and seasons and stuff. I think about it more as a collaboration or a cultivation, or like the reason I gave a gardening example is like, to me, this is exactly gardening. Or it's like brewing beer or cheese or baking or many other scenarios that humans engage in where you don't have control over everything. So in gardening, you can't sculpt the flower into the shape you want. I mean, there are certain like grafting techniques and whatever, but generally you have control over like moisture and sunlight. And you don't really have control over the sunlight part unless you're using grow lamps and whatever. But generally, like, you only can control the ingredients, and the materials are doing the rest. And you're in like a constant dialogue. You're adapting, it's adapting, you're trying to adjust. And through that collaboration, amazing things can happen. If you look at food, for example, look at like McDonald's, where like millions of the exact same thing are industrially produced, to like super nuanced chefs, or like people baking or wine or whatever, which are true collaborations with the medium that are never the same. Over and over and over again, they make different things, and we love that diversity and complexity of the material and the region and the environment that it grew. Like, I don't think we would give that up to say like we're going to standardize all those things. So there is that entire spectrum, and I think of our project more as that, like a collaboration with those forces in trying to cultivate and promote certain things to happen, but not having complete control. And in some ways it's like a living organism. Like I remember going to the Maldives for the first time and thinking like, New York or Miami or like any of these, they've got it all wrong. Like, we're screwed. The Maldives is going to outlive all of us, because these islands are super dynamic. Like, they are moving tens of meters in months, like changing, growing, morphing. And there's like this researcher, Paul Kench, has done all these studies about how these islands have moved over hundreds of years and actually grown in many cases. Even as sea levels are rising, these islands are getting bigger. And like, these are literally living organisms, in like, the definition of it, although the island doesn't, have a nervous system and heart and whatever else, but it's super dynamic. And so our static man-made infrastructure is like doomed, because everything else is dynamic. The environment, the weather, the storms, the animals around it, and so they're all kind of working in this ecosystem. And so we're trying to basically promote these dynamic transformations or assembly. In terms of the marine environment, that's something we need to study more, but we have environmental teams from the Maldives on our project. And so we're trying to monitor it. Like, one of the things that we were just talking to the company that manufactured the large bladders about is that they have certain textiles that can promote different marine life. And so we have all these underwater videos of our thing where there's just like fish and stingrays and all this marine life populating, and it's kind of in the middle of the lagoon. Like, you wouldn't typically get that, but by having these structures there, you have all these like nooks and crannies. And in some ways it's a lot like coral, that it basically promotes marine life to start to like populate it. But I think we can go further. And so one of the things we're looking at is like how to seed the geotextile so that it can both like produce vegetation and promote marine life habitat. So, I think that's something we have to study. And obviously we're like trying to be super conscious of like any negative effects that are possible from basically anytime you do anything, you can have negative effects. And we, want to be responsible about those things and try to study it. But we're definitely not trying to control nature, but rather like dance with it.
I have two more questions from Burchin and Liam. Burchin, why don't you go for it first? You're open for sound.
Hi, Skylar. This is Burchin. And thank you for the presentation. I'm a big fan of your work. So my question is about, I was wondering what your take is on open source learning and projects, and if you're a part of any one of such projects.
Yeah, I'm definitely a big supporter of open source technologies, and obviously, like through my academic hat, my students take advantage of that all the time, and I think anything that can advance knowledge transfer and collaboration stuff is great. It's not a priority of ours or like some main emphasis of our research, and I think most of that is just because let's say on software side, like, we don't produce software tools that, are anything other than get the job done for the things that we want to do. And so, oftentimes like you have groups that like their whole agenda is to make open source tools. And so that just like hasn't been our agenda. And we often are, the project is the most important, and whatever the software is possible and available, and whatever design tool we have to build, or whatever little like code we have to make, or whatever electronic thing we have to do, like we're just making stuff to try to realize that project. And so often we don't like turn that into some like open source thing, but we're not necessarily against it. I just wouldn't say it's like a main agenda of ours.
Okay, thank you. Liam, second to last question. I have one after that. Go.
Hi there. So you've maybe been discussing this in the bits throughout the presentation, but so the self-assembling chair was really remarkable to me for how it demonstrated the compatibility of self-assembly and some, I think you call it arbitrary forms that come from human culture. So, and maybe like how you described your lab as playing with material, but could you just talk about in general how you think about the act of bridging the space between material science and human culture, like making these like kind of beautiful changing objects into things that are useful to society?
Mm-hmm. Yeah, awesome question. And I think about that a lot. I think about that also in relationship to like my computer science background. I was super fascinated. It was like self-taught. I taught myself how to write code when I was in architecture school. Like I wasn't just like a nerd writing code, at 5 years old or something. Like I wasn't that kind of kid. I wish I was, but I was like teaching myself how to write code in architecture school, and then went to computer science, and, was super fascinated by that. And, looking back on it, a lot of the things I was learning in the computer science classes, like, really were not interesting. I was like very, very bored by that. And I wasn't interested in like making the most efficient algorithm that could, save the most amount of memory, or like whatever, compute the fastest, or solve some engineering problem. So, every time I was taking these classes, I was like trying to bring it back to figure out what I could do with it on the design side. And I became much more interested in like fundamentals of computing and information. Like what does it mean to compute? What does it mean to have logic? Like early days of AI and computing and stuff. I became like much more interested in like information theory than I was in like, just writing software or something. And so I guess I think the same thing about material science, that like, we're definitely not computer scientists in the sense of like what most people, I have a degree in that, but like we're not writing software all the time. And the software we're writing is like not particularly sophisticated. And I love that. Like, so Ben Fry is a good friend of mine, and he teaches in our program. He invented processing language. And the reason they call it a sketch is because literally like he and I talk about this, that like the sketch is like literally what he means. Like, I think coding should be sketching, like messy and quick and dirty and wrong and have mistakes. And like, and when I was writing code, like I kind of sucked at it. And so that's what was cool about it. Like I thought I was good at the time, but like looking back, like I was no one compared to like most of the people that can code really well. But it was all these like weird glitches, and I'd be like, whoa, why did that happen? And then I would go like deep down this rabbit hole of mistakes. And then I learned a lot through those mistakes. And so I like was able to creatively like sketch through these medium. And so anyway, I think like a lot about the material science side is in the same way, that like we need to leave room for the mistakes and the sketching and the playing and the experimenting and discovering, and like just being kind of dumb about it and like not knowing every little detail and just being fascinated about it and be like, wow, why does that happen? And then you learn along the way a lot of the technical reasons that these things are happening. You become more and more and more informed. But I think there is something to being, you know, a novice with a curious fascination and like an ability to experiment and play. And like, yeah, we're not experts in material science. We're not experts in computer science. We're not experts in robotics. We're not experts in like environmental engineering, you know, or like landscape engineering, coastal engineering. We're not experts in like many of these things, but we're able to like collaborate with different people, and we're able to like think critically about them and learn and play and experiment, and through that, you know, make some advances. So to us, that's like a good combination. But some people like, yeah, hats off if you can be like a crazy expert in any one of these things, like awesome. You know, we're more like collaborative and strange and curious, you know, or something like that.
That was great. Thank you, Skylar. I guess the last thing I want to ask is probably something you probably won't answer too much about, but you know, MIT has the most cryptic application process for a graduate program of any architecture school.
Really? That's funny.
Yes.
I want to
Our
talk to you more about
students-
that afterwards. I want to learn
Yeah,
more.
exactly. Our students always are chasing, and we do actually have a number that go often, but I have to say, like when they apply to you guys and they apply to SMARCS, and then, you know, then they somehow are chasing after usually the computation lab. I'm assuming that's you, but it's unclear that that's actually you, or if it's 12 other people in different labs, and how many spots there actually are. And I'm just curious if maybe you could give us some of the insight or knowledge of how does a student find their way into your lab? I know Kate did it, and I think she also did it circuitously. I don't think it was a direct.
Yeah. Yeah, I mean, there's not really a direct way. And so now I sort of know what you mean. So yeah, you know, we have there's MIT, and then there's different schools at MIT, like the engineering school, whatever. Ours is the School of Architecture and Planning. Under that, there's multiple departments. So there's Media Lab, Architecture, and Department of Urban Studies and Planning. So the Media Lab is this whole beast. I'll, you know, maybe talk about that for a second, but I'm under the architecture department. Under that department, there's different discipline groups. So computation is one of those. And then there's urbanism, there's architecture design, there's history, theory, criticism, Islamic architecture, building technologies. I might be forgetting one, but like there's different discipline groups. And so the faculty are divided across these different discipline groups. And then each one of the faculty, you know, may have their own research or their own lab, like I do. So I sit within computation and architecture and design. So I'm in two different discipline groups. It's basically just a way that the department divides, you know, different degree programs or different researchers and different faculty hires or whatever else. But when people, so we have undergraduates, when undergraduates apply, they apply to MIT, the institute, and then they choose their major, and they can choose a major in architecture or in design. And I direct those programs. When master's students apply, MArch students, they apply to the Department of Architecture, the Masters of Architecture program. When post-professional master's students want to apply for a research degree, they choose a research topic, which is one of those discipline groups. So computation, AD, history, theory, Islamic architecture, building technology. Like they choose to apply to one of those groups. And then there's PhD programs in some of those too. But when you apply, so no one can apply to my lab, like because my lab doesn't offer a degree program. So I'm a faculty and I have a lab full of researchers and stuff, but you have to be in MIT to do research with us. And so often people like think they can apply to us. And I'm like, just get into MIT any way you can, like whatever program you want. And then you can do research with us. But like, I can't get you in. I have no power in, like you can't apply to my lab because I don't offer a degree. the Media Lab, and so also in our department, like you apply and there's a pool of people and you submit an application with a portfolio and all these other things. And then there's admissions committees and, you know, you're selected. In the Media Lab, which is another department that, you know, I've done research there and stuff, but I'm not affiliated with directly. You know, you apply to the Media Lab, but you select a group, which is a lab. So like you would want to apply to Neri's lab or something. You then essentially apply to her lab directly, and they select the students directly to those. And it's because at the Media Lab, your whole degree is a research degree with a lab. And in our program, you do a research degree, like when Kate came, like you choose your curriculum, you choose what you want to do research on, you choose your advisors, like it's all about the student. It's like totally free and open for them to like set their research interests and their career. And they're not tied to any lab, any agenda, and like they can choose their own agenda. And you know, because of that freedom, that's what allowed me to come up with my own interests, my own research agendas, and then kind of like propel a career. And you know, I think that works for many people, but it's very open-ended. They don't have to do research in a lab.
And so students who apply to the Media Lab, they're actually applying very specifically to a very specific group. And if that specific group doesn't need someone or doesn't take them that year, they're out. But if they applied to SMARCS or I think you call that, right? The SMARCS program, and then they have a computational interest, put that as their choice, they may make it in through a different route and then can choose whatever they want to do when they get there. They may or may not end up in the Media Lab because you could still get a job working for NERI, I suppose, if you wanted, right?
Yeah, you can still do. And what's cool about our program is in computation specifically, like it's so open-ended. Most people get dual degrees, or you can take classes anywhere across campus. You know, not many people take that many classes in the architecture department, you know, a handful, but a lot of like most of my classes were in like AI or the Media Lab or computer science or whatever. People are going to biology and mechanical engineering, material science, like all sorts of different places. Because they're trying to develop like different skills and different research agendas, and you can go anywhere across campus. But yeah, when you apply to the Media, I think the Media Lab is a lot more like, you know, Akim's group at the University of Stuttgart or ETH Zurich with Philippe Bloch or Monsieur Kohler, any of this, where you're really applying and working within a research lab, like one specific group on, you know, their agenda, and you work within that team. It's more like an office environment in a way.
That's very helpful, actually. I hope some of the students who I know have chased after MIT for that. I think they may sometimes make mistakes. Anyway, fantastic lecture. Thank you. It's great to have you virtually here with us. And I know the students and faculty, everyone appreciated it. And thank you everyone for attending. And we will have more lectures coming up. We'll release that data soon. We've been kind of busy with the competition due tomorrow. So we're working on that as a team. Anyway, so thank you, Skylar. Awesome. Thank you, everyone. And I hope you all have a great evening. And Skylar, I'll talk to you more later. Okay, ciao. Thank you, everybody.
Thanks so much.